start off by saying it's kind of interesting times, obviously. This is something I have never, ever even heard of. I had never even heard the last time something like what we're going through right now happened was 102 years ago, 1918. There was a outbreak of the Spanish influenza. And it's interesting, actually, the government in that time enacted a lot of the same kind of rules. So no gatherings of over 10 people. Of course, those of you who know me well know that my family already has 10 people. So we're right on that line. And come June, we'll be over the line. So we'll be in violation just in our own home. I know that the government wouldn't really be serious about that, but it's just kind of funny that we're just right there on that line. And anyway, all these speculations and regulations and panic and everything else that's going on is a little bit unsettling. And so I am constantly of late turning to God and just spending much time in prayer, and I hope you all are too. I'm sure your parents are. We're all a little bit nervous about what's going to happen. None of us wants to get sick, obviously, and more concerning is people that are actually, high risk and stuff. So, and apparently this particular virus spreads really, really fast. But there's still hope, and we have obviously uncertain times, but we all know where to find hope. And so I continually I spend time in the Bible and studying, see what God has to say about things like this. And He's got lots of places in the Scripture, almost more I've heard. There's Finn. I've heard that the Bible says more times, do not be afraid, than anything else. Not than anything else, but it says just many times throughout scriptures, do not be afraid. And Isaiah 41:10, I believe it is. Let me just read that to you. Isaiah 41, verse 10. Fear not, for I am with you. Be not dismayed, for I am your God. I will strengthen you. I will help you. I will uphold you with my righteous right hand. And me and my family, we actually, through our little Sunday school program we do at church, we have a song that goes along with that. Maybe I'll sing it to you sometime, but not right now. I'm not going to humiliate myself that badly. And I don't think it would sound that great over Zoom anyway. But you can actually, we do sing it on my YouTube channel, which is a new thing. Interestingly, all the things that all the changes are actually forcing certain things to happen. And one of my family goals for the year was to actually start a YouTube channel. And so I did that just last weekend. For the first time, I posted my first YouTube video. We recorded our little Sunday school lesson for the 2-year-olds, 3-year-olds, and 4-year-olds from my church. So they would actually be able to kind of sort of do Sunday school. So that was actually a really cool thing. Okay, I'm hearing funny noises all of a sudden again. Did I lose somebody?
It said Finn left.
Finn was here and Finn has left. Oh, man.
I'll check my email, see if he said anything.
It's Davey. Davey's unmuted.
Was that a puppy?
No, it's one second.
Okay, when you do actually when you do unmute to say something, make sure you go back on mute. Now I can actually, and I already did it, I can actually mute everybody from here. So if you start talking too much, I can just mute you. Unlike class, I can just say, in class, I can just, hey, listen, be quiet. I don't have to do that here. I just push the button and you guys can't see. The power. Okay, anyway, I want to go ahead and let's pray and thank God for being with us in crazy times. And then we'll jump into talking about science stuff and get off of this talking about virus. I'm kind of tired of that. So anyway, pray with me. Lord God, we just thank you for this day you've given us. We thank you for your great provisions for us. We thank you that you have promised that you will be there for us, that you will uphold us, and that you provide for us. You bless us as long as we are following you. And just pray that you would help each one of us to trust in you, to lean on you in uncertain times. Pray for all the students and their families and their parents. You'd keep them healthy, and that you would just give them comfort, reassurance as they adapt to new learning things, and as we all try to figure out how to make life work for a time. And we long for the fellowship of being together in the same room, and we learn how valuable that is in the next few weeks. But we also just pray that you would quickly grant our nation deliverance, and we just pray that at least some people would repent and turn back to you as a result of all of this, that our nation would see a revival, and just ask that you would forgive us as a nation. As far as sim science goes, I ask that you would help us to finish out the semester the best we can. Thank you for everybody being willing to be flexible and try new things to figure it out, and just bless our efforts. And we all do this ultimately to honor you and to please you. And we ask these things in the name of Jesus Christ. Amen. All right. So speaking of trying new things, we are, as you already know, in module 13, and we don't have Finn back. I said about homework that you can just turn it in sometime today. I think everybody already heard that. So that's kind of going to be the plan. So if you can get it turned in by Thursday, and then we'll do checking it on either Friday or Thursday evening, and make sure that if we're missing any, graders can work on checking the work now, if you want to, or if it works better to do it at a later time, that's fine too. We can totally be flexible. I'm going to be flexible with y'all students. If you're having a hard time with uploading files, just let me know. Let's just keep, if we're having any issues or difficulties, challenges, the biggest thing is just going to be to communicate, okay? That might be Finn coming back again. There's Finn. I actually see him now. Hey,
Yeah,
Finn.
his Wi-Fi crashed. That's what he said.
Don't crash the Wi-Fi.
My Wi-Fi stopped working, and then my mom didn't wake up till or not wake up. She didn't get out of her online classes till 8, and I didn't get the link. So sorry.
All right, you're good now.
Very important question. Are pajamas allowed to class?
Absolutely.
Great.
What? Wow. Okay.
If you're okay being on camera in your pajamas, bring it on.
I'm gonna wear an emoji bathrobe next Thursday.
I usually sleep in
You
my
do
clothes
that.
anyway, so
That's a guy thing, right, Henry?
That is definitely a guy thing.
It saves so much time to just, you don't even have to bother with that. You wear the same clothes for like 5 days too, and we don't care.
Prefer being clean.
You prefer being clean? All right. Well, I guess I do too, to be honest with you. But it's fun to joke around about it. And anyway, all right. Let's jump into talking about some science stuff. I was saying I'm going to be flexible, Finn. I'm going to restate a couple of these things because you weren't in here, I think, when I was saying it. But I'm going to be really try to be flexible with y'all as far as getting your homework in and stuff like that. The big thing to me is just going to be communicate. You communicate with me, and probably best if moving forward, if you ask me for an extension by sending me an email or something like that, then you probably should copy the teaching assistants also, so they can be informed of. I'll try to, when I answer, I'll try to reply and include their emails on there so everybody can be in the loop. We're going to have to really rely on our technology stuff to make sure we're communicating. I have a suspicion that this may be our meeting format for the next several weeks. We might get to have our year-end party, but I don't know. I mean, I'm kind of thinking that most of the month of April is going to be in this format. So as best we can, as long as it works. And so it's not going to be there's definitely going to be some problems or some things that aren't going to work very well, that don't work as well as being in the classroom settings, obviously experiments, but I'm working on some stuff that'll help do that. Some of the experiments will be demonstration suitable, and we can actually even do some of them on over this format. So we can all do it together, a couple of the experiments that we'll be able to do. And so we're going to do the best we can. And so the key is going to be communicate. Just as with many other aspects of life, the more you communicate, the better off everybody will be. All right, so we have a little over an hour before we have to kick out of here. And so I'm going to jump into reviewing some of the notes. Let's see how well this works. I'm probably not going to be able to see all your lovely faces once I switch over to the slide, and you don't get to see any fun animations like we do in the regular class, but you'll get to actually see the notes.
So today is my brother's birthday, and we're going to be doing breakfast at some point. So is it okay if I hop out, if I let you know?
Yeah, just mention it. Come on the audio. So that's probably what you'll have to do if you want to try to get my attention, is just unmute and ask a question if you have a question, and we'll let's give this a whirl. So here in a second, you will see pop up on your screen. Okay, I can see some of you. Actually, I can scroll through the whole list here. All right. So let me know if anything's not showing correctly. I'm going to actually skip through a bunch of this because these slides several of them are the ones we've already seen, but it makes me start at the very beginning. And this is how it's going to work, is it's just going to be kind of scroll through. Just do a quick review. if you recall the structure of an atom, the basic components, the electrons, the protons, and the neutrons. That should be easy to remember. The electrons, the smallest component, lightest, they have a negative charge, and they orbit the shell in the orbital shells. This is all review. Protons are larger than the electrons, smaller than neutrons, 2,000 times more mass than the electron, positive charge, and they're in the nucleus. Neutrons. Okay, the neutron is unstable by itself. Remind yourself of that. Structure of the atom. All right, here's the key thing. I'm just going to review this. Remember, the atomic number is the number of protons in a nucleus. The mass number is the sum of the protons and neutrons in the nucleus. Don't get those two confused. Isotopes. Remember that within an element, you can have different numbers of neutrons, but the number of protons is always the same. If you change the number of protons, you now are talking about a different element on the periodic table. So that's isotopes and elements. Excuse me. All right, the atomic mass is the average mass of atoms in an element, and it gives us some kind of an indication of some of the mass number, remember? So if you remember, you might actually need your textbook, because I don't have a periodic table that I can actually put up on the screen. Let me, and actually, I just realized my textbook's in the other room. Let me go get it. I'll be right back.
Guinea piggy.
Why?
Yeah, like you've had a guinea pig this whole time?
Yep.
Bro,
Well, actually, I switched out the guinea pigs, but
Do you have a pen and pencil?
a guinea pig of all things.
Here's your grapefruit.
What do you need?
Who has a guinea pig?
Here's your notebook. Take one.
Is it with you right there?
Somebody's gonna put notes.
Yeah.
Sarah has a guinea pig. She just like brought one.
I have 3 of them.
Okay, that's just weird.
That's 3 more than I have.
You have to have at least 2 because they're social animals.
I should have brought my bunny.
Your bunny?
Are we showing off pets?
Oh yes, get
Show off
Shasta.
for science class. It's just show off your pets.
I'll get Shasta.
Get
I'll
Shasta.
get her.
Sorry.
You've already derailed the class. That's okay. I
There
can
goes Sterling.
I can get it back. Okay. One of those boring parts about physical science is Bohr models. We went over that at length in the last class. I think you guys made me draw something like unununium or something like that had 452 electrons. Not really. I don't remember which one we did. It was like copper or something. All right. So that was, so anybody have any questions about Bohr models and the electron shells? Speak now or don't.
Yeah, it was kind of confusing. Study
Bohr
guide,
model?
but yeah.
Speak now or forever hold your peace.
It was copper that you drew last week.
Oh, was? Wow. Good memory on my part.
No, I wrote it down.
I did too, but I erased it.
I have acquired Shasta.
Up. Up.
She doesn't. She can't hear anything.
I know, but she is a pup.
Is it a cat? I can't see it.
No. Hey,
It's a corgi with extra fluff.
The doggo.
Adorable.
Shasta!
What's his name?
It's a girl. Her name is
did
Shasta.
you just assume my dog's gender, Lily?
No, I said it. So I didn't really
It's
assume
Shasta.
anything.
Her name is Shasta,
Shasta pup.
and she's really fluffy.
Well, I have a box of nerds.
Oh, because we're nerds?
Oh, bro.
Yeah, if the shoe fits. All right.
Possibly.
So somebody said something about the Bohr models are a little bit confusing.
That was Sterling.
Yeah.
Okay. I'm not going to go through an entire Bohr model, but I'll do this real quick. We can look at in your textbook on one of the pages.
Do I need to flip to that page?
It's page
Yes.
324. There's one at 324.
Shasta,
324,
it's
yep,
time
that's
for
the
you
one.
to leave.
There's also one at 323.
323. Oh yeah, there's a Bohr model, but let me let me draw something here for you. Let's try this. Clear the screen. And then the Bohr model is going to look something like this. You will have the nucleus, and I have to draw that kind of ugly like that. Actually, it looks kind of like a guy wearing a ball cap. There's his ear. Okay, anyway, so that is my nucleus. That's going to be where your protons and neutrons go, because the Bohr model is more about the electron shells than it is about the nucleus. So then the electron shells are something like you have your electrons and they're orbiting around the around the nucleus. And then the first orbit, if you look at the table that's on page 324, the first orbit has a capacity of 2 electrons. So that's why I just drew 2 little electrons in here. Then you have the second energy level, which can actually carry 8 electrons. So we could actually draw 8, and the humidity is high, so my finger's sticky. And 5, 6, 7, 8. Don't worry about my distribution. So the second energy level would have 8 electrons in it. And then the third energy level, which I'm actually not going to draw, can hold up to 18. So in your first 2 energy levels, you can have up to 10 electrons total. So that is going to get you up through, and remember, the number of electrons is going to be equal to the number of protons. So that can get you up through element 10, which is neon. So anything that actually has an atomic number larger than 10 is going to end up being in the third. It'll have the electrons in the third orbital shell. So you can have up to 18 in the third orbital shell. So that gets you up to element 28, which is nickel. And so if you one more than that, copper, which is the one I drew the last time, has 1 electron in the 4th orbital shell. And so you can go up to 32 in the 4th orbital shell. So that's how the Bohr models work in essence. So you just keep filling up the shell. Once it's full, you bump up to the next energy level, and then you fill up that shell and then keep going up to the next energy level until you have the number of electrons equal to the number of protons, or the atomic number of the element. So hopefully that clears that up a little bit for you. All right, so now let's talk about, remember, let me just do a back up a little, another step. You actually took your quarterly test already. So your quarterly test is about the 4 fundamental forces, and we've only covered 3 of those up to this date, which is the gravitational force, the electromagnetic force, and the weak force. So that's as far as we've talked so far. And so now we're going to actually talk about the 4th one, and that is going to be obviously the strong force. So these slides are so much more fun when you got your animations and I can put the points up there one at a time. So, but let's just talk through this just for a couple of minutes. What components are in the nucleus of the atom? Well, we've already discussed that. It is protons and neutrons. So the neutrons have no charge. Protons have a positive charge. And if you recall, opposite charges attract by the electromagnetic force, and like charges, what do like charges do? They repel. I have to answer my own questions on this format. I don't like that.
You can ask us if you
Not to
want us to
unmute.
answer.
Right.
Just throw someone under the bus.
I said it aloud but forgot to unmute.
Okay. I'll take your word for it.
I'm a witness. I'm a witness. I heard her.
Okay. But okay, so like charges repel. So, and if you remember the rules with regard to forces, the gravitational force, the electromagnetic force, what happens to the force as the objects get closer? If you have two objects that are interacting with each other with the force, whether that be two massive objects interacting by the gravitational force, or if that is two electrons interacting, repelling each other by the electromagnetic force, what happens to the force as the two objects get closer?
It gets stronger.
It gets stronger. And remember, not only does it get stronger by the square of the distance between them. So if I take two objects and then I take the distance and cut it in half, then it actually, the force gets bigger because they're closer, but it not only just gets bigger, it gets bigger by the square of the distance. So going from here to here actually increases the force by a factor of 4. And then if I cut it in half again, then I increase the force by a factor of 4 again. So that's 4 times 4. So this, if you cut the force or cut the distance to 1/8, then the increase in force is a factor of 16. 4 times 4. Does that make sense? Okay. So the point I'm making is, if you're familiar with exponents, the force increases on an exponential curve. So it's going up as the objects come closer, and it's going up exponentially, which means the closer they get, the more that force increases. So if the force is, say, 1 or let's say the force is 10, whatever units we're using, 10 newtons or something like that, when the objects are at this distance, and then we cut the distance to 1/8, then the force is now 160 times greater. So that's an exponential. Cut it in half, and the force is 40 times. Cut it in half again, which makes it 1/8 from where it was originally. The force is now 160 times, or 160 newtons. I said I started off with 10 newtons, then cut it in half, and it's 40 newtons. Cut it in half again, it's 160 newtons. 40 times 4. We cut it in half again, so it's 1/16, then it's 160 times 4. So every time you do that, every time you cut the distance in half, the force magnifies greatly. So the point is that those like charges are repelling. In the nucleus, you have protons, which are like charge. And how big is a nucleus? You know, is it a couple of inches, or is it so small you can't actually see it even with an electron microscope? That's
Teensy tiny.
It is teensy tiny. So we've cut that distance from the electromagnetic force. Remember, the electromagnetic force works over a short range, so maybe a few inches. We can actually interact with an object, say up to maybe 2 feet or something like that with the electromagnetic force. We have some really crazy strong magnets, like the ones they might use at a steel scrapyard, the ones that are hooked to a crane and the magnet is bigger, this big around, and they go around and they pick up cars with those. So those can have a effective range of maybe a couple of feet, and obviously the strength of the force isn't great, but so that's the range, the maximum range of the electromagnetic force. But the nucleus of an atom is extremely tiny, so those protons are all packed in there, extremely tiny, and each one is repelling the other protons. So think about, if we keep cutting that distance from 2 feet down, cut it in half to 1 foot, then to 6 inches, then to 3 inches, then to 1.5 inches, and then keep going, keep cutting it in half until we get to the size of a nucleus of an atom. We cut it in half a whole bunch of times to get to that tiny space, right? So that is every time you do that, the force goes up by a factor of 4. So the force, by the time you get to the spacing of a nucleus of an atom, the force, the electromagnetic force repelling, trying to throw the protons out of the nucleus, is going to be a big number. So what are you going to do? What do you have to do to make the protons stay in the nucleus? You have to have a force that's stronger than that electromagnetic force that is working over that extremely small distance. And that's when we get to the strong force. And it's that strong force that holds the protons in the nucleus of an atom. So should be pretty impressive. Unfortunately, we don't get to actually talk about what the real numbers are, but those numbers are going to be, well, you could think of it this way. The numbers, the amount of the force that is necessary to keep the protons in the nucleus of an atom is going to be equally as impressive as the smallness of the nucleus itself. That's one way to think of it. So that force is extremely high. Like, well, when we start talking about nuclear fission, we'll get a little bit of an idea. We can split the nucleus of an atom, and we can generate enough energy by splitting one atom to power your household light bulb for a very, very long time, simply because there's so much energy stored because of the strong force. There's so much energy that the strong force has to overcome, has to exert in order to hold the protons in that teeny tiny space. All right, so the strong force, as it says right there on your screen, works through the processes of particle exchange. And we've talked about that before. We did the little experiment with the graviton theory, if you recall that, where we were trying to toss the ball back and forth. And it was very obvious that the particle exchange, or that process of particle exchange, was difficult the farther the two objects got apart. This one, the strong force works through the process of particle exchange. And interestingly enough, now this is really beyond, again, like we talk about all these things, that the concepts go way beyond the scope of 8th grade physical science class, which, you know, many aspects of science go way beyond any high school level classes. But this idea of particle exchange is been demonstrated. They have done experiments to actually prove this is what it does. So even though we cannot see the size or measure, well, we can actually calculate the size of a nucleus of an atom. Even though we can't actually see those things, we actually have been able to do experiments. Scientists, really smart scientists, guys, have been able to do experiments that demonstrate effectively or definitively that particle exchange is the mechanism by which the strong force works, as well as that is also the mechanism by which the electromagnetic force works. All right, so the particles used in the exchange are called pions, which that's, I think, probably everybody's favorite. And just funny names. What were they called? The particle, anybody remember what is the particle that is exchanged to make the electromagnetic force work?
Photons.
Photons, that's right. So photon's a package of light that acts like a particle. So it's actually not even really a particle, it just pretends to be a particle. Pions are actually a particle. They're not photons. They're something different. And I believe it says that, oh yes, the bottom of page 325 in your book, this guy with the fun names, it sounds like Hideki Yukawa, proposed the nuclear force occurs as a result of the fact that protons and neutrons exchange tiny particles with one another. And in his initial theory, he called them pions, and actually made a rough prediction of what their mass should be. This is 1935, so this was a long time ago that scientists figured these things out. 1947, the pions were actually discovered by experiment, and their mass was indeed close to what Mr. Yukawa had predicted. Yukawa's explanation of the nuclear force revolutionized our understanding of the nucleus, and as a result, he was awarded the Nobel Prize for Physics in 1949. So he actually did math and predicted what the mass of these pions. So they're particles that actually have mass. Photons, as far as I understand it, don't actually have mass. They're just pure energy, but they can actually act like a particle. So pions, on the other hand, have some mass. So when the strong force is acting between two protons, it actually acts between the protons and the neutrons as well. But so when the
I got birthday breakfast now.
Oh, all right. Are you going to come back, you think, or?
I don't know. It'll probably be over by the time we're done doing presents and such.
Okay. Well, as soon as I find out what the link is for the YouTube of this session, then I'll let you know.
Okay, I'll go back and watch it.
Okay. Thanks. Have fun. Tell your brother happy birthday. Oh, she's gone. She probably didn't hear that. I tried. So in case you're really missing Sim Science later, this will actually be available on YouTube. So if you just can't get enough Sim Science, then
This whole thing is gonna be on YouTube.
I understand it. I don't know exactly what it'll look like, but it might be
Wait,
just
will it
what
have all of us in it?
it's actually recording right now. So
That's gonna be like YouTube section because we'll be on YouTube saying that we're on YouTube. Like for example, hello watcher, I am on YouTube.
Breaking the fourth wall.
Oh man. So if I just need to look at the camera more so I can break the fourth wall more, right?
Mr. Sears breaks the fourth wall.
I didn't break the fourth law though. The fourth law of thermodynamics, or the fourth law of Newton's gravity. I'm making stuff up now. Okay, so here's the other point there. The pions are very short-lived, so that particle exchange has to happen very, very quickly, and since they don't live very long, the range of effectiveness of the strong force is really the size of the nucleus of an atom. So just to go back and recap and pull everything together, the gravitational force can work, and its range is, say, the diameter of, or the radius of the solar system. Actually, it can actually work over longer spaces than that. The gravitational pull, or gravitational force in our solar system, actually not our solar system, actually works over the span of the Milky Way galaxy. So it's extremely, extremely long range. Well, compared to that, which, by the way, the Milky Way is like 100,000 light years across. The range of the electromagnetic force, we said, was maybe a couple of feet. So exponentially smaller than the range of the gravitational force. The range of the nuclear force, or the strong force, is exponentially smaller than the range of the electromagnetic force. So its range of operation is like the diameter of the nucleus of an atom. So really, really short range. And that's why, it's because the pions can't exist out in open space. They have to actually get to the other particle, or the other component that they're exchanging with. So again, part of this doesn't make a lot of sense to me because I'm not a nuclear physicist and I haven't studied to that level. Is what causes the protons to want to exchange these particles? But I'm content to know that this has been proven, that is how the strong force operates. All right, and then this was one of my favorites right here. See, this is an animated little clip, and I don't think I can get it to animate in this program. I was trying yesterday and I couldn't figure out how to do it either. So you'll have to be content with my description of the animation, but this has Jerry the mouse. Jerry the mouse right here. Let's see if I can do this.
I love Tom and Jerry.
Tom and Jerry is
Spotlights. See,
Yes.
Jerry the mouse here. He throws the pie into Tom's face. So it seems to fit with this subject we were talking about, which is pions. So pie on your face, All right. So moving on.
Funny.
It is actually, and y'all would have been laughing if you could actually see the animated part, and I wouldn't have had to explain it. So it really, it's kind of like explaining a dad joke. If you have to explain it, you don't bother because it's just not as funny. Wait, are dad jokes even funny anyway?
Yes.
Yes, they're
Don't
funny
you
when
dare
executed.
question.
They're the funniest jokes.
100%.
They're funnier than mom jokes.
Wait, moms have jokes.
What's up?
Bonus
Off the stage.
bonus points. Bonus points. Everybody gets bonus points. All right. So, but if you have to
Yay.
explain the joke, it's just not as funny. That's just a fact of life. All right. So let's go on and talk about the couple of more points on the strong voice. The strong voice. I'm just going to leave that. I'm going to say it the wrong way. Manifestation of the strong voice in the nucleus is called the nuclear voice. The strong force is also what holds quarks together, which make up neutrons and protons. So subatomic particles. Quarks are interesting. And quarks exchange particles called gluons. So those are also a funny name. Interestingly, the names of all of the particles that are used in these different forces all end with the word ONS, or the suffix ONS. I guess may not actually be a suffix, but we talked about gravitons and the gravitational force, which we actually don't know if those exist. We talked about photons, and then pions and gluons. So all four of those particles end in ONS. So that might help you remember them when it comes up on a test or something. All right. Oh, you guys probably already saw that, didn't you? Okay, let's wait on that for just a second. I want to actually tell you about another place where you can actually learn some more information about the subatomic particles and quarks and leptons and antineutrinos and all kinds of fun little things. The quarks, there's actually six different kinds of quarks. It's like up, down, charm, strange, and I can't remember the other ones. They're like tall and short or something. No, it's not that. And they actually have what's called color charge, and their charge is like 1/3 and -1/3. It's very complicated, way more stuff to know and learn. But there's a website that you can actually go to that's actually kind of fun, and you can learn a little bit more about it. So if you're interested in just looking into it, you don't have to actually delve into it at great detail, but this little website is kind of fun. You can get on there and just explore around a little bit in your spare time. And in the past, I've actually offered my students a little bit of extra credit if they want to do some research on this website and write me a brief little 1-page report on that. I've actually done that before. So if that's something you're interested in, I can probably offer that again. But the website anyway is called Particle Adventure. So you can either Google Particle or Adventure, or I think that you can say it's particleadventure.com. Let me check and make sure that I've got that right. I know it's Particle Adventure or Particle Adventures. Let me see if I can find it real quick. I see, particleadventure.org. Yes, that's the place. And it's got little animations and it's not from a Christian perspective. does actually talk a little bit about evolution stuff. So you got to take some of it with a grain of salt, obviously, as with many other things, not only just science, but don't get me started. The thing about it though is for the most part, it's just dealing in facts, things that have been experimentally demonstrated, the existence of quarks, and you can look at all the little different names and read some about color charge. It's interesting if you're fascinated by subatomic particles, or if you just want to know some more stuff. So, and if you want to do that and you want to write me a little 1-page paper, I'll give you some extra points somewhere for that, because I like to see students who want to learn a little bit more, and I like to give you a little incentive to do that. It's not something that's got to be real detailed or highly theoretical, but it's kind of just give you something else, learn a little bit more. And then you can go around and impress your friends by the fact that you know the name of the 6 different types of quarks and where they exist and what's their particle exchanges and things like that. So yeah, extra nerd points for what it's worth. I do those kinds of things. All right, so let me do this. Let's throw this up here. And this is going to be a little bit different. I have some questions for you. And so I want you to close your books. This just really close your books and just let's see how you do. So if you would scribble down the answers to these questions on a piece of paper, and then in a minute we'll walk through all of them and see what the answers all are.
Are we doing an online pop quiz?
Online pop quiz, you got it.
Just when I was thinking, man, we haven't had a quiz in a while.
Why now?
Perfect timing.
Henry jinxed
Perfect
it.
timing.
Look at what
Yeah,
you
you're welcome, guys.
did.
It's my fault.
Good job,
Yes.
Henry.
Henry emailed me last night and said, please, Mr. Sears, can we please have a quiz tomorrow? I really wanted to see what an online quiz would be like.
You should have
You
seen how
have
hard I
betrayed
picked.
the group.
He didn't really do that. This was on here. It's if I hadn't looked at it already, I would have been surprised by it too. No Googling it.
If he sees you typing, you will be banned from Google.
You can't even leave the Zoom session without, to Google anything without actually leaving the meeting. So.
Yeah, you can.
That's why you own a computer.
Finn knows because he's doing it.
Ooh, you got him good.
That's not me. Somebody's off mute.
I think it was Sam.
It was Sam.
Was he
Jinx.
tapping out the answers in Morse code to everybody?
Sam.
Darn, why don't I know Morse code?
Ugh.
That was,
Tis
I don't know
unfortunate.
Morse code. I don't know Morse
Sam
code.
was actually saying Morse code for please help me. I don't know what I'm doing.
Oh, okay. Somebody please
Got him.
text me the answers. All right. Can you see all the questions on your end?
Are we going to be graded on this?
Oh no. We are, aren't we? Your silence
Answer
is disturbing.
me.
No. Are you faking being muted? Oh, Sam, by the way, I saw the reflection of your Fortnite account in your glasses.
That's not Fortnite.
What is it?
That would be my Breath of the Wild account.
Breath of the Wild is better than Fortnite.
That's true.
Anything is better than Fortnite, to be honest.
Anything is better than Fortnite.
Like donuts?
Way better.
Yes.
Donuts are the best.
Only Krispy
Like-
Kreme.
I don't like donuts
Debatable.
very
Fun.
much.
Very debatable.
You're not a human. You don't like donuts.
My kids were suggesting that I grab a snack while I'm in here teaching. So, like, have some of those honey buns with all the frosting on them.
Just so you can rub it in our faces that you have a snack and we don't.
Yeah, I mean, I could actually eat some of my. I do still have my nerds here. So,
Someone get me some
and
pretzels.
it's full. Never even opened yet.
Okay,
Somebody get
look at,
Cedar some pretzels.
look at question number 6. It says, what is the charge on in proton?
Man, who typed that?
That's a typo.
Gee, I wonder who typed
Sorry,
that.
it was me.
Sucks to be
Sorry, that was
guy.
me. I made a typo. All my fault.
Whoever typed that should actually get a bad grade on the quiz. All right.
Just
so,
kidding. It was not me.
All right, so let's do this. Let's just walk through let's go through and answer the questions, and you'll just check your own and see how you did. And then everybody can just shout your score out all at once. No, actually, what I'm going to do, this is for your own benefit. So you self-assess on this. You see how you did and see if you're studying like you should. Okay, so this is not going to actually, I'm not going to actually take this for a grade or record this in our grades.
But it's going on YouTube.
Oh, that's true.
Do we get extra credit for yelling it out?
We may have to
No, you'll
edit
get
that part out of the
bonus
YouTube.
points.
Extra credit for yelling it out now. Oh, for yelling out your score?
The answer to everything is 12, always.
No, it's not.
Answer is Jesus.
I was going to say, if you're in Sunday school, the answer is either Jesus or God, but that's actually not true either. So,
Or Jesus Christ.
The answer to the question is 42.
So what is the answer to the atomic number, Mr. Answers?
42.
No.
I know.
The atomic
Claire,
number
what is it?
The number of protons in an atom.
There we go.
Yay, I got something right.
Ouch.
Check your answer and make sure you got it right. Okay?
I said protons and neutrons in an atom.
Yeah, see, that's the one that is the one that always snags people, is that atomic number versus the mass number. Okay, so what's an isotope? Claire knows the answer. Let's see if anybody else does. What's an isotope? All right, Claire, I got no takers.
The atoms with the same number of protons but different number of neutrons.
That is correct. So if you got that answer right, you're super smart. All right. What is a radioactive isotope?
Me,
Who knows that one?
Lily,
Lily, go ahead.
an atom with a nucleus that is not stable.
That's it. All right. What is in the nucleus of an atom? Michaela.
Protons and neutrons.
Protons and neutrons, not photons. If you wrote photons, that's not correct, and you would not get credit for that on a test. But protons and neutrons, that is correct. All right, so who wants the mass number?
Brady does.
Brady?
The sum of the protons and neutrons.
That
in
is
atom.
correct. All right, and who is criticizing my typo there on the and proton?
Sterling,
I
It was
wasn't
actually Henry.
criticizing, I was
Henry.
just pointing it out.
I said nothing about how bad the typing was. I said it
So-
was my fault, then I took
Which
back
counts?
the claim.
Sterling, what is the charge on N proton?
I couldn't answer that question.
You didn't?
No.
Do you know what the charge is?
Is this a number answer or is this
No.
something else?
No. It's not a number.
Oh, wait, do you mean positive or negative?
Yes, but that's not the correct answer if you said it like that.
I was
Positive.
trying to figure out. I didn't exactly know what it wanted.
Okay.
And then we
Positive.
started going over answers.
All right. The charge on a proton, I think Finn was saying it there, is positive. So we don't quantify the charge. We don't talk about how do you measure the actual charge. So we're not looking for a number. If you see a question about charge, other than calculating how much the charge might change on if you change or how much the force changes as a result of change in the charge, but they just tell you the charge doubles or the charge went in half or something like that. So, all right, and the last question, which is bigger, protons or neutrons? Who knows that one?
We're raising our hands.
I can't see all of you.
Is there? Finn knows this one. Is there a way to say it without having to announce that you know it? That's just like flexing on everyone.
Yeah, well, yeah, I mean, no, actually not really. You if you know the answer and you say the answer, then you're pretty much telling everybody that you know the answer. So which is the answer, Finn?
Neutrons are bigger.
Neutrons are bigger, that is correct. Now that's flexing right there. The little dance.
He wrote it down earlier or on the slide.
Okay. So everybody check your answers and make sure you if you see a deficiency there, then you can work on making sure you study that stuff so you get it correct for the test that you're supposed to take on this theoretically tomorrow. All right, then let's just keep moving on and get through the rest of our notes. All right, radioactivity. This is fun stuff. We have to be out in 17 minutes.
Okay. Now let's talk. Ready?
All right. So radioactive isotopes, that was one of the quiz questions. What is a radioactive isotope? It is an isotope with a unstable nucleus. I guess that should be an unstable nucleus. Since somebody's going to correct my grammar. Okay, and if you remember, we even reviewed it before at the beginning of our time today. We reviewed that neutrons are unstable by themselves. So if you have too many neutrons or in some form or fashion, usually it's too many neutrons and it needs to get rid of a neutron in some form or fashion, which causes it to be radioactive. Now cue the song. Radioactive, radioactive. Okay.
Please, no.
When was
I
that
used to like
song
that song.
released?
I
Like
used to.
2012?
I could probably
think
cue
that's
it up
right.
on my phone.
Do it.
Do it.
Well, that's okay.
Do
Let's
it.
make,
Radioactive.
let's make sure we get through the slide.
Radioactive.
Or else everybody's going to be, if I start doing a bunch of singing stuff, then everybody's going to skip class next week. I'll be teaching myself.
I
It's
definitely
funner
would.
when you
Just
sing.
gonna leave the Zoom.
Okay, so let's talk about the different types of radioactive decay. And then we'll do a couple of little example problems. And I think that's probably going to be all we got to cover. So, all right, radioactive decay. The first one obviously is alpha. It's pretty easy to remember. These are the Greek letters, alpha, beta, and gamma. So those are the three types of radioactive decay. So the first one is alphabetical order, alpha, and then beta is the second one, and gamma. And I'm not sure if gamma is the actual third letter of the Greek alphabet. If anybody knows Greek, I'm not that much. It's not that good on it. It's all kind of Greek to me. All right, so alpha decay is the first one, and it is when the nucleus emits an alpha particle, as it says right there, which is a 4He nucleus. And for bonus points, who knows what He stands for?
Brady does.
Shout it out.
Lily does.
I do too.
So what is it?
Helium.
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 Yeah. Helium.
Okay, bunch of bonus points going out there.
Yeah.
Okay, what is the number 4 in the front of that helium stand for? Claire, what is it?
The number of protons and neutrons? Or is that
Yes. What's the other name for that?
the atomic number?
No, it's not the atomic number.
It's the mass number.
Who is that?
Lily.
Lily, yes, you're right. It is the mass number.
Great job.
Okay. Say what?
I'm congratulating Lily.
Oh, okay. Okay, that is the mass number of it, and it represents 2 neutrons and 2 protons. Okay, and the daughter product for alpha decay has 2 fewer protons and 2 fewer neutrons. So your atomic number that is actually those signs on my numbers there are incorrect. I'm pausing like something's not right there. The atomic number is actually -2 and the mass number is -4. I should fix that. So we go
You
here.
can draw on your screen, right?
So this one should be a negative and a negative there. So your mass number decreases by 2. Oh, somebody else is drawing on my screen.
Wait, how do you do that?
Yeah.
Done it.
How'd you do
Who
that?
gone and done it?
I thought only I could see that. Sorry.
That was you?
Yeah.
Cedar.
Guilty as
The
charged.
doer of the crime.
Peter, how did you do it?
There's a little pencil button on the screen. Oh, we could leverage that as a learning up how to do this.
Wait.
So I could actually write questions on here, and somebody else has to write the answers. Now, if I push the clear, I can wipe out everybody's.
I don't see the pencil.
I'm gonna read the bottom one in my Sandos voice.
One, I don't see anything, and two, now that that knowledge has been passed on to the general public, everyone's using it.
I can't figure out how to use it, so don't worry.
No weapon.
Well, it may not be available to everybody. Some of us, if you have, I'm running on an iPad, so if you're running on a tablet or something like that, you may
I'm
have
on computer. I've noticed that a lot of the settings you guys have don't show up on.
Yeah, I'm on an iPhone.
Oh, okay. So it's very tiny for yours. Yours, the screen is very tiny.
Yeah, your face is about a centimeter long.
Wow.
It's a pretty short face.
I shrunk. Okay, let's, so this, I need to fix that. This should be -2 and mass number of -4. So, and then alpha decay is the lowest energy form of radioactive decay. So let's just practice with this one real quick while it's on there. Let's go whiteboard mode. And let's just pick a, make up an isotope. Actually, you guys have these on your own questions somewhere, don't you? Daughter product of alpha decay of 2:41 a.m. Oh my goodness. That's early in the morning. 2:41 a.m. That's a little harder to do than it looks.
It looks like an H.
Trust
Yeah.
me, I know it's hard to draw with a mouse.
I'm using my finger.
Oh, that's even worse.
I don't know about that. Yeah. There we go. That looks better. So AM is americium. Its atomic number is 95. Yeah, I can write better with a not a Sharpie, one of those whiteboard markers, obviously. Well, let's see if I can make this a little bit better. All right. So its atomic number is 95, which means it has 95 protons and 95 electrons. And then the number of neutrons is going to be 241 minus 95, which would be 146. 146 neutrons. I'm just going to put, somebody leave?
I don't think so.
How many people take this class?
No, yeah, one participant is gone suddenly.
Is there 16 people?
It's supposed to be 16 people.
Who is
Okay,
Casey?
well let's stay on this real quick. It might have been one of our assistants. All right, so 95 protons, 95 electrons, and 146 neutrons, because we're about out of time. So if we do alpha decay, then this actually goes to 93 protons, which would be 90 and 93 electrons, and 144 neutrons. So the daughter product would be, let me get some room over here. The daughter product is going to be element number 93.
I know that element.
What is it?
Neptunium.
Yep, NP.
Nerd.
Okay, so I have a heads up. In one of the study guide questions, when we were finding daughter products, and I was doing the problem, when I got my answer and I had the atomic number, I went and looked around in the periodic table to figure out which symbol had that number, and none of the symbols on the chart had that number. So I checked the teacher book to see, I'm like, all right, what is it? What am I supposed to find? And it was something that wasn't even in the periodic table.
Really?
Yeah. Like I looked around, I couldn't find it anywhere.
But did you also look at the proton number? Because you have like, the mass number will vary, but if you know the proton number, because that's how I found neptunium, I just looked on the periodic table for the top number for the protons and electrons, and yeah.
No, I'm not talking about the number, the numbers. I had the numbers, but I looked around on my periodic table and like the letters, it was like R something. It was R and another letter. It wasn't even on this table.
Was it RU?
I think so. It might have been.
With the whatever.
It was R something, and it wasn't there.
If it's RU, then RU is number 44.
Yeah, I see it there. I think it was like RA or RT or something.
I remember RN.
Yeah,
It was on the study guide.
too. And that's, well, I have the study guide right here.
Yeah, I don't know if I just did the math wrong or if that specific.
I'm pretty sure it
not on
was
the chart.
RU.
Let's see.
Yeah, I don't have my study guide with me, and it has the correct answer on it now. So
Okay. Well, I have
yeah, there's like 3 minutes left.
yeah.
Did you buy like the extended time? Because you can
Yes,
do
we
that.
did.
But yeah, like the thing with Zoom is like once the time for the meeting runs out, it just cuts it off.
Yeah, no, we don't have to cut off, but we do have, there's going to be another class that's going to try to join. So if I go a couple minutes over, it's going to be all right, but we do need to try to wrap it up. But okay, so the key, Sterling, is to look at the number of protons, and then you match that up with the atomic number, which is the top number as it's shown on the periodic table. It's the one in the box on the very top. And then you use that to find the chemical symbol, and then you can look that up on the table in the inside front cover of your book.
Yeah,
So-
I checked I checked both the number above and below it on the periodic table, and it wasn't there.
So what I was thinking is you might have actually been looking at the mass number and not the atomic number. So, or you did a math error, that's possible. But even if you had a math error, you should have been able to find the
No,
chemical.
I don't think I did have a math error. I think I just couldn't find the letters.
Okay. Well, yeah, it's you look at the numbers. Use the numbers before you look for the letters. The letters are all kind of jumbled up in there. So, in any case, to answer this question, and this was one of your on your own questions, so you already have this one. So this is 93 protons, 93 electrons, 144 neutrons, and so the daughter product would be a 2. It's going to be the number will be 4 less than the original mass number that was given, which is 241. So the new mass number will be 200. Oops, I wrote a 3, not a 2. Silly fingers. 237 neptunium or neptonium, whatever it is. So that's how you do the beta decay. Alpha decay, sorry, that's alpha decay. And remember that alpha decay is the lowest energy form of radioactive decay. All right, we're not gonna have time to do the beta decay example, but this is beta decay. It happens when a neutron, remember unstable nucleus, a neutron emits an electron and becomes a proton. So it turns itself into a proton. And so your daughter product is going to be change of in the atomic number of +1. That looks like a +I. That's a weird looking one. But, and the mass number stays the same. So your mass number doesn't change. So in the previous example, if we did 241, if we did 241 AM, then the daughter product will be 241, and then we need to look at the next letter up, which is CM, because it's going to have actually 1 more proton. So that would be the daughter product of beta decay of the previous example. Okay, so it's going to be +1 proton. But since the neutron becomes a proton, it just changes, then you don't change your mass number. All right. It has a higher energy than beta. Man, somebody needs to really check this stuff. All right, higher energy than alpha decay. And then finally, gamma decay. The nucleus emits a high energy photon, and the number of protons and neutrons does not change. So gamma decay does not produce a daughter product. It does have the highest energy radioactive decay. So that one's going to take the most stuff to actually stop it. So I'm just racing through this because we're 2 minutes over, and here's the last slide. All right, danger of radioactive decay. The author of the book goes into great detail on this, so you can actually read that. If you haven't read it, you need to read that. Make sure you understand. But the danger of radioactive decay is just like the danger of a lot of other things in life, in the world. It's all about concentration. It can actually do damage if you have a high exposure to it. And then the radioactive dating, and then I have this comment on here. Okay, there's some calculations on half-life. I can make, if you want me to, let me know. I'll make a short video on calculating half-life at some point, and put it up on YouTube or something like that. Send you a link to it, or you could probably Google it and find a better production than what I can actually do anyway. But then there's the radioactive dating. I'm sure you've talked about this before. They talk about carbon-14 dating in the ICR. The Institute for Creation Research has tons of resources that talk in great detail about effectiveness of radioactive dating. But the radioactive dating is all about the assumptions. They assume the amount of carbon in the environment at a given time. And yeah, my last comment there is testimony to my dad. That's my dad mode there. But in any case, I know we kind of scrambled through the tail end of that. And we don't have any time to do any of the calculations for half-lives and things like that. But I think that's pretty straightforward. You just keep cutting it in half, and each time you cut it in half, it takes the same amount of time. So I think carbon-14 has a half-life of 5,700 years. So if you start off with 10 grams and half of it will be gone, so you'll be down to 5 grams after 5,700 years. And then after 11,400 years, you'll be down to 1/4 of what you started with, or 2.5 grams. And then another 5,700 years would be down to 1.25 grams, and so on. So that's kind of a really quick run through on half-lives. And then radioactive dating. I encourage you to look into some of the research that Institute for Creation Research, or probably Answers in Genesis with Ken Ham, that is his group. He's going to have some good information about radioactive dating. So anybody have any questions or comments right before we kick out of here and turn this over to the next group?
Who is Casey?
Casey? Oh, that's
Of the pink screen.
Casey Jones from Ninja Turtles.
Casey
No.
Jones.
That's Mrs. Bauer, right?
Yes.
I was listening in, so just seeing how it's going for when my son does his class later this afternoon.
Yeah, that's right.
Hi.
He's in biology, right?
Correct. But I have really bad morning hair, and so I have a little tab over my picture so you can't see me.
Me too.
Oh. Yeah.
I've got a couple of my beard's hairs that's sticking up here. Oh, and my gray really shows good on the camera.
It's okay, Mr. Sears.
I actually got lucky today. This is my morning hair.
Yeah.
You look pretty blurry to me, so.
My morning hair.
Everybody's
That's why
screen is like a couple inches wide here on mine.
It's why I'm wearing a hat.
Look at Finn's hair. It's so short.
Mine's still shorter than Finn's.
True.
Good point.
Mr. Sears conquers all with his short hair.
That's right. Don't forget it. All right. Well, I think we got to get out of here. So thank you all for jumping in, and it was actually kind of fun. And I guess we'll do it again next week. And I'll be praying for you and your family. Stay healthy and so forth.
Will the link be the same next week?
I believe it is.
We can use the same email as this week?
Yes.
Okay.
Yep. And
No,
I
it
will
won't be late.
resend file upload instructions next week, and on Monday or so, along with the work assignments that you have to do. So
Also, when and how will we get our grading things back or our assignments?
I will, whatever we actually mark up for you that actually has a mark grade on it, I will send to you by email. So like your experiment reports and things that we have to grade, I will send by email to you. And I guess that's pretty much it. So whatever stuff needs to go back to you, your homework assignments, that's just a completion grade. So we're gonna check those and record it, and you don't have to have those back because you still have them hard copy. So
What about like the quarterly, the test?
the quarterly test, I will grade that, and I'm probably gonna grade them on the computer, and then I'll send them back to you by email once I get them all graded. Any other questions? All right, well, y'all have a great rest of your day, and I will hopefully see you all, see all your faces at least next week in the same place on the same channel.
All right.
All
Signing
right.
off.
See y'all. Have a good weekend.
Bio condigos, amigo.
Goodbye in Russian.
Fuego, Kokentaku.
Adios.
Or then
Adios
you could just say the classic bye.
Adios in Spanish.
Or you can say goodbye in Russian.
If you
Bye
know
in Russian.
Oh,
Signing off.
See ya.
Are you just like clicking us off?
No, I'm not. Everybody's leaving.
Okay.
There's a leave hangout button in the bottom right, and I'm waiting to be the last. I don't know why. I just wanted to do something final.
Well, I can actually just boot you all out at the same time, which I got to do now. So I'll see you all later.